Okay. All right, let's go ahead and get started. I'd like to welcome you to the Kent Weekly Pavement Seminar. It's my pleasure to introduce today's speaker, one of my PhD students, Brian Hill. Brian has run the full gamut. There is currently doing that here at Illinois, having done his bachelor's here and master's degree. He was supported by a Federal Highway Administration Dwight D. Eisenhower Graduate Research Fellowship, which is a long title and a pretty prestigious award during his master's, and now is supported on an NSF project that's trying to innovate in the area of preventing cracking in pavements. And so he's working on the experimental side, kind of at the interface of the experiment and the modeling. So he'll talk about one of the techniques we're trying to develop to understand cracking in asphalt a little bit better. He was also a recent recipient of one of the Walter K. Parr AAPT scholarships, Association of Asphalt Paving Technologists. So he'll be receiving that award in April in Denver at the AAPT annual meeting. And Salman was the other award winner, so we're lucky to have two here at ICT and ATRL. So please join me in welcoming Brian.
All right, thank you. Welcome to the seminar. Hopefully you guys find it interesting or at least intriguing. It's a bit of a long title. Basically, as Professor Butler said, just trying to develop digital image correlation to kind of evaluate fracture and bulk low temperature properties of asphalt materials. Just kind of a brief outline of what I'll discuss, kind of where we're at in the state of the practice with low temperature asphalt characterization, with evaluating deformation, then getting into digital image correlation, the different methods that people use in terms of analyzing it or analyzing source and target images, the current research objectives that we have with the NSF project, and then kind of getting into the configuration that we have at ATRL. Every DIC configuration is a little bit different depending on what your methods are, what you're trying to evaluate. So I'll get into specifically our cameras, the orientation of the system, and then I'll kind of get into, I'll start with some asphalt binder testing that I did with Salman in regard to creep and fracture, and then finish up with asphalt mixture testing in terms of the IDT creep and DCT fracture energy results that we evaluated. So in terms of asphalt mixture low temperature characterization, in general we always use strain gauges, okay, and those in general have been very good to us. We've really implemented those in many cases, and we've improved them quite a bit. And if we're looking at low temperatures tests, we're specifically dealing with AASHTO T322 and using epsilon gauges, which are very sensitive, such that we can measure micro inches worth of deformation, or using CMOD gauges, as these plots show with fracture tests, whether they be DCTs or SCBs or SEBs. And obviously they have their applications. They allow us to have closed loop control on fracture energy tests. But the main problem that we have is that they only provide us results at discrete locations. So if we're only looking at discrete locations, we really don't have an idea of what's going on in the full field. Specifically, we're making assumptions in terms of what those full field deformations are with regard to whether we're assuming it's linear elastic, fracture mechanics are available, or whether we can use like nonlinear methods, stuff like that. So if we're going to move beyond that or try to improve upon what we're doing, digital image correlation is a good way to do that. It's an optical technique. Optical techniques have been around for a long time, whether it be photoelasticity or Moiré interferometry. Obviously, we know that those have some issues with them, specifically dealing with heterogeneous materials like asphalt. But when we get into looking at digital image correlation, it seems like it can produce some very good results. I kind of borrowed this figure just because I think it really shows exactly what's going on. It doesn't have to be a fracture specimen. We've used digital image correlation in other areas of asphalt. Other researchers have used it dealing with uniaxial compression tests. And basically all you're doing is you're just taking a CCD camera or a high-powered SLR camera such that you can be able to take images of a specific region of interest and look at it at one point, and then after you load it or after a certain period of time, you can analyze how much deformation that specimen has gone through, and specifically evaluating the full field characteristics and allowing you to measure the direction and motion of distinct features. And those distinct features are the speckle patterns, and I completely forgot, but I was going to bring in a specimen of mine, but basically all we do in order to apply a texture pattern, in order to use digital image correlation, is take a specimen, we just paint it black, and then we just put a white paint speckle pattern on it. And in general, that can give us a good range of values. If we're using like an 8-bit image from 0 to 255, we generally get a good gradient between the pixels such that we can characterize the different subsets that we have within the image. And in terms of the requirements that we need, number one being a good surface treatment. Some digital image correlation techniques say that the surface treatment isn't that important. Originally, we tried to use no surface treatment. We felt like if we didn't use a surface treatment, because we had asphalt and we had aggregate and we had mastic materials, that we might not have to use it. But if you're dealing with, say, a limestone aggregate in an asphalt mixture, you see a lot of pixel values that are close to 255. And specifically if you're using, say, a 12.5 to a 19 millimeter nominal max aggregate size mixture, you could be dealing with an aggregate that takes up quite a bit of your image, that ends up affecting your ability to correlate well, such that your cross-correlation coefficients that we'd use in digital image correlation are kind of lost. And then looking at the camera equipment that we need in order to have acceptable resolution and speed, again, that gets back to what test you're going to use. If you're going to be doing like an E-star test, you need a completely different camera than what you would need for maybe a monotonic fracture test at low temperatures. In terms of the method of analysis, I'll only describe two different methods of analysis. There are multiple methods. In general, in asphalt, we've kind of seen 2 to 3, sometimes 4, depending on how much you dig into the literature. Specifically with a subset method, in general, if you see like VIC 2D software, VIC 3D software that was developed in South Carolina, that uses the subset method. And this is kind of a pictorial representation of what the subset method is. It was used in early DIC applications in asphalt, specifically at NC State. It's also used in fracture characterization at University of Nebraska-Lincoln. It has its good and its bad sides. I guess the biggest issue that they see is the dependence on the speckle pattern. In general, it shouldn't be that hard to produce a quality speckle pattern. If you use a spray paint and you're careful about it, you shouldn't have any issues as long as you're not wiping your hands over it. But the biggest issue that I've seen, I guess, other than the speckle pattern, is the lack of continuity between the subsets. If you're paging across from subset to subset, specifically if you look at each one of these boxes, if you kind of consider them as elements, you can see the displacement jumps that you have between each one. And you can think about it, if you had displacement jumps, then you're going to have huge discontinuities between your strain values, such that with like an asphalt material where you're dealing with quite a bit of heterogeneity, you'll end up having like a checkerboard pattern with your strain fields, which is something that you really don't want to see. So work that's been done in the past, specifically by Dr. Ben Shen at UIUC with Professor Paulino's group, he dealt with using a full field method, and he applied that to functionally graded cementitious materials. It was developed in the past decade, and the good thing was it was developed by the same guys who developed this method, so they knew that there were some issues with the subset method, and they furthered that research. And in general, with this region of interest, again, now you're not seeing these little elements in between each one. Now you're specifically looking at points such that there's a given constraint saying that, okay, we need to make sure that we have good continuity between each point such that we don't have large jumps in displacement. Because really the only time that you should see large jumps in displacement is at a discontinuity where you're driving a crack through your region of interest. So to kind of get into the research objectives that we have with the NSF project, First things first, we really want to look at both conventional and thin bonded overlay pavement sections. This schematic, which was developed by Dr. Sarfraz Ahmed, he did a lot of work in experimentally evaluating thin bonded overlays. One of our research partners in this project, as it is a goalie project, is Road Science. Road Science does a lot of work in developing asphalt systems such that you can create a thin overlay and avoid having reflective cracking or transverse cracking that you'd generally see with an overlay system in the field. I'm mainly going to focus on conventional asphalt systems, or quasi-homogeneous. I don't want to say homogeneous, but they're not anywhere near a thin bonded overlay system. In essence, a thin bonded overlay system is just a thin asphalt pavement that has a gradient in its asphalt binder content. All they're doing is placing a heavy tack coat at the bottom of the layer, and then as they place, they immediately place the asphalt concrete on top of that, and you have an upward wicking of the asphalt binder into the section. Salma's done also quite a bit of work with this in terms of evaluating interfaces, and they developed the CT test for this. And then finally, I guess the major point of the research is coupling DIC findings with FEM approaches to reverse engineer quality asphalt systems. We talk so much about using green technologies and using RAP and RAS and warm mix asphalt and biobinder, but one big push the NSF has is reverse engineering materials such that you can use these materials, but such that they're really sustainable. Because if we're creating a pavement system that really is saving us money up front, but it's not saving us in terms of performance, then we're really hurting ourselves in the long run. And within the finite element approach, again, I'm dealing more with the experimental side. So we're working in conjunction with Professor Paulino and one of his students in developing a rate-dependent cohesive zone model to be able to apply with the digital image correlation technique. So in terms of the current DIC configuration that we have at Atrial, it was really a trial and error process. A lot of testing that has been done with digital image correlation, specifically with asphalt, dealt with testing at closer to room temperature. So you didn't have to deal with putting a camera inside of a chamber or thinking about putting a camera inside of a chamber. When we're dealing with testing at minus 12 degrees C, it can be a problem trying to put a SLR camera or a CCD camera inside of a chamber, or even putting an LED light inside of a chamber, because you're dealing with moisture changes, moisture falling on top of the light source such that you're changing the amount of reflection that you get in the background, and then all of a sudden you're changing the pixel intensities and you're not able to correlate as well as you'd like. This is kind of a loose schematic of what's going on, and neglect the fact that that camera is backwards. Basically, either with the Stingray F201C, which I'll describe in a minute, or the other camera that we're using, which is a digital SLR, we're looking at both the full field and the near tip properties, or the deformation properties, such that we can understand what's going on when we drive that crack through the material. In general, we're using dish-shaped compact tension fracture tests. In terms of the cameras, we have both a Canon EOS 5D Mark II, and so that has around 21 megapixels. It's spec'd out at 3 frames per second. In general, we can't get any more than 1 frame per 2 to 3 seconds, which with a fracture test and asphalt, in general, you're dealing with hitting your peak load around like 5 to 6 seconds. So if you're dealing with that, you're really only getting 2 images, which can be a problem. So for the most part, we're dealing with creep testing with this camera, but we are definitely going to be using it in our fracture characterization. It's just that right now, the Stingray seems to be working the best. Obviously, we do have a drop in the resolution. The frame rate, obviously in some digital image correlation techniques, they're using cameras that can go thousands of frames per second. We don't need to go that fast. In essence, if we can get 30 to 50 images pre-peak, then we can easily understand what's going on post-peak when we have maybe a 2 to 3 minute test that really, for the most part, those 2 or 3 minutes are all occurring in the softening zone. And then in terms of the LED lights, originally we were going to place the LED lights all inside of the chamber. Recently I decided that it seemed like it was working better if we had LED lights inside and outside the chamber. And those pictures of the system are kind of shown here. There's a lot of clutter in the images. But essentially this is just our Instron controller, the cooling chamber. I have an LED light set up outside. It is kind of pointed at an angle. I have the camera directly perpendicular to the surface of the specimen. I make sure I use a level every time, making sure that I don't have any angle to the camera face. Obviously, if you do have an angle there, you may not be able to tell it, but you're going to be able to see differences in your deformations if you ran more than 3 to 4 specimens and you saw a drastic difference between them. You can easily use stereoscopic digital image correlation. That's something that we're probably going to move towards in the future, but right now we're focusing on a single plane rather than looking at it from an angle, which is the easiest way of applying digital image correlation. One thing that I do want to note, though, is that we did kind of see some issues initially. If you do use an LED light source coming outside, if you're using loading arms for a DCT specimen, you can somewhat get a little bit of a reflection there. And if you're dealing with reflections, then you have to be careful because, well, not reflections, shadows. If you get a shadow there, obviously you're going to have a problem with the pixel intensities that you have. In terms of the pre-processing and post-processing operations, we gather all images as raw image files, and then we convert them in pre-processing to TIFF files. In digital image correlation, you always want to stay as close to the original image file as possible. If you're compressing the image into a JPEG or some other file format, you're really going to have some problems in terms of your resolution. We generally deal with removing rigid body motions, rigid body rotations. We're finding better ways to handle those. And then also removing that region of interest, which is generally just outside of the crack tip. So then obviously going through and processing the source and target images, knowing that we have the same region of interest. It's just whether or not, or the distance and time between the images that we took, and then finally post-processing, retrieving the data and analyzing it, whether you're retrieving it and analyzing it through MATLAB or a commercial software, that's up to you. In terms of the asphalt binder tests, again, it was work that I did with Salman. Salman developed the test. I just kind of thought it'd be interesting to take a look at asphalt binders in general. If you're going to look at digital image correlation with asphalt, it makes it a little bit easier dealing with an asphalt binder at a low temperature because that's probably about as homogeneous as you're going to get with an asphalt system. We ran IDT creep and fracture tests. With the creep tests, as I said, we used the Canon EOS camera. And I forgot to mention this, but we do use a macro lens so we can eliminate the barrel effect that you would generally have with that type of camera. The image acquisition rate was 1 image per 10 seconds. It's a 1,000-second test. So if we're taking 100 images, we felt like that was probably about the right speed that we needed. The analysis region or region of interest was around 2,000 by 2,000 pixels. We used a slightly higher creep load than you generally use for an asphalt binder. That's a little bit high at -12, but we found some interesting results. And then with a fracture test, we used the other camera. The rate was approximately 5 images per second. And the region of interest was quite a bit smaller, obviously, because we have less resolution with that camera. And the rate of loading was 12.7 millimeters per minute, which is what is specified in analyzing the IDT strength of an asphalt mixture. So in terms of these results, I have probably 5 or 6 slides. I'm just going to kind of page through them fairly quickly, just so that you can get an idea of what we saw. As you can see, I mean, it looks fairly good. I mean, from what we'd anticipate for an IDT test, and kind of what we've seen in the past, or what we would have expected to see based on literature. Whoops. Yeah, you can generally see that it approximated what you'd expect for like a homogeneous body. In terms of the fracture, it was fairly interesting. I'm sure someone could tell you a lot more about this information, but essentially we were able to catch as close as we possibly could to the fracture. It was a very dynamic fracture, it was very quick. So for us to be able to handle picking up that fracture, specifically at the point of initiation, it was a little bit difficult. And as you can see in the onset of loading, we generally found an odd state of deformation. But again, this was probably 0.2 seconds after we initially loaded it. So whether it was irregularities within the material, right before failure though, we found some very good results. We found that in several different specimens, we found different locations for where failure occurred. In terms of the more important or more interesting results, as far as I would think in terms of the mixture IDT analysis, I analyzed mixtures that I developed in my master's thesis. One was a virgin HMA mixture, one was a 45% wrap HMA mixture. Both used PG6422. Their VMAs were approximately 15.3% in the mix design, and I kept the percent effective binder the same so that I could kind of make a fairly good comparison between the two mixtures. I used a pretty high creep load, but it seemed pretty close to what I would anticipate with generally using strain gauges. Test temperature was at -12°C. Same camera, same image acquisition rate, slightly smaller analysis region. If you can see this, in general, we saw that the light source over on this side was a little bit too bright, such that we were seeing a little bit more white values than than what I wanted to see. So I neglected that region as much as I possibly could. And in terms of the HMA results, I'll pan through those results too. The wrap results were very similar. The only difference was that the magnitudes were less, which is what we'd anticipate. In general, we'd find that we'd have lesser deformations if we're dealing with a wrap mixture that was including 45% wrap, which was probably around like maybe 25 to 30% of the binder content was taken from the wrap material. So as you can see, it doesn't look as nice as the binder results. I wasn't surprised by that. Obviously, you're dealing with a 9.5 millimeter nominal max aggregate size mixture. But in the end, you are seeing similar results to what we'd anticipate with the HMA, which led us to looking at the strain in the X direction. And this is times 10 to the -6, so these values look fairly high. And you can tell that the virgin HMA definitely had much more strain in the X direction. I would point out that there was a little bit more scatter in this data. These aren't exactly straight lines. I found a few data points that were odd in the past 2 days, and I deleted them because they were fairly high and fairly low, and they didn't really describe what was actually going on. In terms of the DCT results, which is really a major part of this research, I looked at a 45% wrap HMA and an Evotherm WMA mixture. Both, again, had PG6422. I mixed the warm mix asphalts mixtures at 25 degrees C less than the hot mix asphalt, which is the common temperature reduction that you'd find for Evotherm 3G. Standard CMOD opening rate. I used the Stingray camera in this case. The image acquisition rate was 6 images per second, and the region of interest was approximately 650 by 850. And I kind of compare them, one on the left, one on the right. So if you take a look at the image on the left-hand side with the wrap, you can kind of, and on the right-hand side, you can kind of see that this, I don't want to say blob, but this region of deformation extends out, and this is at 20 seconds, so this is after we've hit peak load. You can kind of see that we are seeing approximately the same region of deformation. However, you can kind of see the leaves hanging off, or the, I don't want to say linear elastic regions that we'd expect for LEFM, but in general we saw more deformation in the virgin WMA mixture, which I wasn't really surprised by. You'd anticipate that you'd have more straining in that material, that you probably have just a significantly brittle failure in a wrap mixture as compared to the virgin WMA. And again, I found the same thing going on at 40 seconds. The one thing that we've seen, though, is that the crack seems to reorient itself slightly upon initiation of the crack as it's moving forward. Sometimes it'll go upward, sometimes it'll go downward. It kind of depends on how much rotation and that you have in the DCT specimen. Specifically, sometimes I've seen that you may have holes that aren't oriented the best, and if that's the case, then you can have some irregularities in how that crack propagates initially. Like maybe in the first 5 to 10 millimeters, it will propagate upward, and then it'll come back to approximately horizontal alignment. And again, same type of deal with 60 seconds. And then I plotted radial distance from the crack tip. So essentially, if this is the crack tip, I just plotted on a theta that equals 0 line what the strains were in the y direction at different times. So whether that be 10 seconds, which was immediately after the peak load, or at 40 seconds or 60 seconds. One thing I do want to note, though, is that once you get probably beyond 1,000 microstrain, you're probably not dealing with real material behavior. That's just pure separation in those regions. But you can definitely tell that with the war mix asphalt, you're seeing an increased amount of deformation in the material at every single time interval, as compared to the 45% wrap. So kind of to summarize everything, I think we've found, and I've shown a little bit here, and there's much more research out there that you can take a look at that shows that digital image correlation really is a viable method that we can use in characterizing asphalt materials. We're not completely 100% there. People using digital image correlation for the past 20 years have done a lot of work in ceramics, or dealing with metals, or dealing with plastics. And they've done a very good job at kind of fine-tuning it for their situation. For us, it's a little bit different. We're dealing with material that really behaves differently at different temperatures. But I think I've shown, and I think we can show, that it also can differentiate between different mixtures quite well. And I think it's a viable method to use in the future. I think as we move forward, as cameras get better and better, as we can get cameras that are cheaper, using these in locations, or using these in, I guess, DOT labs, such like they're using with Hamburg wheel trackers now, as they're moving more towards fundamental testing. I think this is a good method they could use to further evaluate their materials. And then obviously further testing is needed to characterize thin bonded overlay systems. That's going to be a little bit of a challenge dealing with a CT specimen. You have a smaller ligament length, and you're also dealing with a material that has even more heterogeneity within it from the location of the crack tip moving forward. So with that, in terms of acknowledgments, obviously thank Professor Butler for his help as my advisor through my master's degree and my PhD. And as I move forward, my research group members, everybody's helped me obviously the HRL staff, Road Science, specifically Marvin Exline, who's a co-PI on the project, and then National Science Foundation. So with that being said, if anyone has any questions.
Okay, plenty of time for questions. Yeah, go ahead.
Go.
Yeah, of course, you did not discuss, of course, you did not cover this aspect because we talked about the experimental features.
Mhm.
But I'm wondering what kind of modeling approaches would be able to differentiate this behavior which we see in the experiment, in the sense that warm aspartic or the recycled aspartic or the virgin aspartic, what are the things, what are the parameters will be different which will cause this kind of different behavior in the experiment?
Is it all right if I draw on the whiteboard?
Yeah, just try to draw big if you can. If you turn on the light.
So hopefully everybody can see this. In general, with cohesive zone models, so you have a traction. I guess I'll just put T as separation. When you look at the local parameters, specifically, and I believe it's a extrinsic model, right, that doesn't have an initial compliance to it. You know, if you're dealing with a hot mix asphalt, say this is HMA or this is a wrap mix as compared to a warm mix asphalt, that peak traction that you have and the peak separation that you have, the traction will be a little bit higher and the separation or the max separation that you'll have will be a little bit lower. But when you deal with a warm mix asphalt, in theory, if it's like a chemically modified warm mix asphalt, not like an organically modified warm mix asphalt like Sasabit, which should behave more like a HMA, you'd expect that you'd have a lower peak traction, that you'd have a larger maximum separation. Does that answer your question?
And the experiments you have shown, is it a single experiment or you also have seen such behavior in a repetitive manner?
Oh,
How was the repeatability?
No, the repeatability's there. I didn't know how. Yeah, I mean, I've tested probably, I don't know, 75 to 100 specimens.
Per category of sample?
Not per category. I mean, I've tested whether it be a hot mix asphalt to a warm mix asphalt or to a polymerized asphalt mixture to a 6422.
Okay, so how much was the variability within the same category?
Variability in terms of what parameters?
In terms of, you, for example, you saw the warm mix asphalt, the strain is larger or than the normal asphalt mix. Did you see the same thing for all the samples with warm mix asphalt?
Not with all warm mix asphalts. In general, I only looked at that one warm mix asphalt type. So I would be just making conjecture about the other types of warm mix asphalt. But like I said, I mean, with a Sasabit type material, I would anticipate that you wouldn't see much of a difference between these two.
One of the really surprising things we found when we started testing binder, I was a little skeptical when Salman did some of the first large-scale binder tests because I thought we'd run out of binder. For one thing, is using 100 times more binder than the conventional super pave test, but luckily we had a good supply on hand. So we started doing DCT and IDT binder fracture tests, obviously at low temperatures. We were pretty surprised how low the fracture energy was for the pure binder. We thought it might be, a fraction of the mixture, because the mixture derives some of its toughness from its the fact that it's a composite. But it was like an order of magnitude, or a couple of order of magnitudes less. So very, very, very brittle, very, very low fracture energy. And so I think what the DIC can help us do is to understand how the aggregate works together with the asphalt to, make it tough for the crack to move through the pavement. And we noticed drastically different fracture behavior between wrap mixes and warm mix and wrap/warm mix and recycled asphalt shingle mixes and fiber modified, polymer modified. The global fracture results are different, but we have a hard time getting insight just by looking at one clip gauge and one load trace. But by focusing in on that full field, we can see how cracks are dispersed and branching, and what are the mechanisms for energy absorption? Why does it take so much energy to drive a crack through certain materials and not much energy through others? I think we'll know that a lot better. So I think this tool, even though it may not, I mean, who knows if we'll ever have a test specimen where we replace clip gauges with cameras. Could happen because the cameras are pretty cheap. Whether we do that or not, I don't think is the point. It's a scientific study just trying to understand the mechanisms of cracking or the mitigation of cracking in various materials, including a lot of sustainable materials, so that in the long run we can start moving in the right direction of engineering these fairly random sustainable approaches where we have a lot of variability to somehow start to get on top of these other approaches and engineer them more precisely. But there's a lot of work to do in the meanwhile, because the DIC, if you just buy a DIC system there's a couple of companies that market them, they'll do a fine job for homogeneous materials and strain. They struggle with heterogeneous materials and strain, and they're almost useless for heterogeneous materials in fracture. They don't identify cracks, they don't analyze cracking fields properly. So Brian has his work cut out to do that, and to work with the modelers in our group to integrate the two pieces.
Go ahead, Matthew.
I just had a question about the setup that we developed basically for capturing images.
Yeah.
So you were showing that you're putting the camera outside of the chamber at the end of
Yes.
the camera, right?
Uh-huh.
So did you guys do some other orientation in terms of how did you come up with that configuration? And somehow another question which may be related to this question is that what was the effect of this image capturing method, or the technique that you used? How did you calibrate your images to see if the camera settings or all of this orientation would affect the images? Because
Sure.
you did not talk a lot about how did you analyze things.
Sure. In terms of looking at whether, how should I put it? So when we're dealing with whether we always had the specimen inside the chamber. It was whether we would have the chamber door open or not, right? In general, with the chamber window or the chamber door closed, we'd be dealing with reflections. That's why I put a black background behind there. I might not have mentioned that. So I put a black background behind it just to make sure that there wasn't any movement within the images, such that if I'm going from my source to the target, then I know that there aren't any issues with relative motions behind there within the target images. Now, in terms of, you said calibration, right? Can you repeat your question? I want to make sure I answer it.
The Delrin plastic test that we did.
Sure. I didn't show any work that I did with Delrin plastic. Delrin plastic is very well known in terms of what its modulus is. It is a modulus very similar to asphalt materials. We went through and measured the Poisson's ratio and the amount of deformation that we'd have, such that we could back out what the modulus was. And we were probably within, I don't know, maybe, was it 3 to 5% maybe?
Yeah, of the textbook value.
Yeah.
So the resolution had an effect on the results? I mean, the image resolution and
Sure, I mean,
aperture, speed, and camera settings.
yes, I mean, those are adjusted accordingly. I mean, initially, we had to, well, number one, I guess, Dr. Ben Shen, he'd done quite a bit of work in this area, so he came in and helped us calibrate it initially, because he knew what to look for in terms of the calibration, in terms of adjusting settings with the cameras. To get into the specifics, I have them written down, but I didn't bring them with me today. But we did have to go through a process to improve upon that, because obviously, I mean, if you don't calibrate it initially, you're not going to get results that make any sense.
Yeah, and this is fairly recent news, but we're going to participate in a RILEM study, kind of like a round robin on DIC. This is part of the RILEM mechanisms of cracking and bonding in asphalt pavements that I chair. But one of the subcommittees is chaired by Professor Gabrielle Tabaldi finish up in the next 12 to 18 months. And the annual meeting, the KO combined RILA meetings, we're going to be hosting them next year. They'll be up in Chicago, September 18th through 20th at the University of Illinois Conference Center, right next to the Sears/Willis Tower. I guess it's the Willis Tower now.
Any further questions?
I have a comment.
Go ahead, Kevin.
I think the images that you showed are very interesting. We used to have these images or strain images, contour images by using FEM analysis or software. Now we have those direct strain images from the real test now. So I think it's a great improvement. And my question is, have you gone back and relate the FEM models that used to predict these strains, and you have to relate them with the actual strains?
Not yet.
Just
Not yet.
curiosity, is it?
Yeah, I mean, that's obviously something that's very important that we need to go through and do. But at this point, we were just trying to get to the point where we could get there with the system. It took 3 or 4 months just to figure out how to deal with getting it inside the chamber and testing it at -12 or testing it at low temperature. But yeah, obviously, I mean, we need to go through and be able to analyze it and at least kind of look at the differences and figure out where they lie between the FEM analysis and what we've been finding. All right. Last call.
Actually, just to follow up on the comment, I think that really makes you think and open your mind to how you can use this to even improve the cohesive zone models and then its prediction. So, because that's what you measure now, you can capture that in the optics and
Sure.
exactly how to predict that from the that's
Yeah, we make big assumptions about the local model. It's more or less just an inverse analysis scheme, curve fitting to back out that model, whereas we're going to be able to see the physics that drive that local model, and it'll be much more physical. It'll be a much better physical representation of what's going on once we know what's going on.
Ready.
Okay, with that, thanks again, Brian. We're going to have special food next Thursday.